let's move ahead to the next talk. It's by Ken Shirriff, who restores old computers, including the Xerox Alto and Apollo Guidance computer. And his talk is titled Looking at Silicon. Ken will explain how to open and study some of the vintage ICs like 8008 microprocessor and the first FPGA chip to 8086 processor, both real and counterfeit. Also, if you have ever visited the Computer History Museum in Santa Clara, I believe, some of the computers out there have been restored with the help of Ken. So yeah, enjoy. Ken, over to you now.
Okay, can you hear me okay? Can you hear me?
Yes, I can hear you perfectly fine.
Okay, great. Hi, everyone. I'm going to discuss how to understand silicon circuits and how to reverse engineer them by looking at some interesting historical chips. So here's the Intel 8008, Intel's first 8-bit processor, and this is how it looks under the microscope. It looks pretty complicated, even though it only has 3,500 transistors. You're looking at the tiny silicon die here. Around the outside, the white squares are the pads. The black lines are the tiny bond wires connecting these pads to the external pins. Most of what you see in this view is the metal layer, the white metal wiring on top of the chip. Underneath that wiring is the silicon, which in this photo looks purple. So with some reverse engineering, the functional groups of the chip can be determined. You can see the basic parts of a processor, the instruction register and the instruction decoder, the arithmetic logic unit, the ALU, and some registers. One unusual feature of this chip is that the stack is on the chip, not in RAM. So now how do you reverse engineer a chip like this and determine these functional groups and how they work? Well, this is the same 8008 die, but with the metal removed. If you want to see the transistors clearly, you can dissolve the metal layer, and I'll explain how to do that later. And then in the red box, I've zoomed in to show 16 transistors. The yellow lines are polysilicon. This is a special type of silicon that forms a wiring layer on top of the silicon die. Regions of the silicon have been doped with impurities to change the silicon's properties to make it semiconducting. The black border between these regions makes them visible. So now let's step back and look at how a single transistor is constructed. Simplified, an NMOS transistor is a switch controlled by the gate. When the gate is 1, the switch is closed, connecting the source and the drain. When the gate is 0, the switch is open. Now there's a lot more to transistors than this, but for our purposes, we can just consider it open and closed. In the picture at the bottom is the silicon die, which is an insulator more or less. Regions of the silicon have been doped to change its properties and make it a semiconductor. These are the pink regions. In between is the gate. A charge on the gate makes the channel between the source and the drain conduct. There's a thin insulating layer between the gate and the silicon. And now this is why MOS ICs are static sensitive. Static electricity can blow a hole through this thin oxide layer. So originally the gate was metal, so the layers of a transistor were metal, oxide, semiconductor, MOS. In 1970, they introduced polysilicon for the gate. So really it should be called a POS transistor, but for some reason that name didn't catch on. So that's how a transistor looks in theory. Now here's what it actually looks like under the microscope. The doped conductive silicon is yellowish, forming the source and the drain. The silicon regions have irregular shapes because they want to pack the circuitry in as tightly as possible. You can see the speckled polysilicon strip that forms the gate on top of the silicon between the source and the drain. So now that we have a transistor, we can build an inverter. The schematic shows how an NMOS inverter is built. One transistor with input connected to the gate, a pull-up resistor at the top, and now the pull-up resistor is actually implemented through a transistor for performance reasons. And on the right, you can see the inverter under the microscope. It's the same transistor as before, but with the pull-up transistor added. Now here's how it works. If you put a 0 in, the transistor turns off. Then the pull-up resistor pulls output high, so you get a 1 out. So it's inverted your 0. And the other case is you put a 1 in, now the transistor turns on. This connects the output to ground, so you can get a 0 out. And now once you recognize transistors, you can start tracing out the circuitry of a chip. Now, here's something more complicated. A NAND gate is like an inverter, except you have two transistors in series. If both inputs are 1, the transistors turn on and pull the output to 0. Otherwise, the resistor pulls the output high, so you get your NAND function. Now, if you connect the transistors in parallel, you get a NOR gate. If any of the inputs are high, the transistor pulls the output low. You can build much more complex gates as well, using the same principles. Now, here's what a NOR gate looks when it's on the chip. This is on the 8086. It's a bit tricky to separate the NOR gate from the neighboring circuitry, but the arrows indicate the key components. You can see the two large transistors, one for each input, and then a smaller pull-up at the top. So the point is, once you can recognize transistors, you can figure out how they make gates. One more thing I'd like to describe is the connections between the layers. In the photo, you see some circles that look like dents. These are vias that connect the silicon to the metal layer on top, or connect the polysilicon to the metal layer. Now in this picture, I've removed the metal layer, so you have to imagine that there's metal wiring on top making these connections. And then there are also contacts, and these connect the silicon layer to the polysilicon on top. The arrows indicate two of these contacts. So now, once you know these components, you can reverse engineer more complex circuits. Here's one bit of the 8086's ALU. On the right, you can see the NOR gate that we just looked at and how it is a part of the larger circuit. I'm not going to go into all the details of the ALU here, but the point is you can work your way up from transistors to gates to functional blocks. Now, I'd like to look more closely at a couple of interesting chips. The HewlettPackard Nanoprocessor is a very unusual processor. HP used it as a controller in their test equipment products. This chip is so simple that it doesn't even add or subtract. Since it's simpler than a microprocessor, they call it the nanoprocessor. Although its functionality was limited, its killer feature was that it was much faster than competing microprocessors and much cheaper too. So it was very good for a control processor. Now, my favorite feature of the nanoprocessor is that the IC production line wasn't completely stable. So each chip had different properties. So they tested each chip and then hand wrote the bias voltage on the chip. You can see that this chip required negative 2.5 volts. Other chips might require negative 5 volts. So each chip had to have the custom voltages that it needed. Now let's look at how the registers in the nanoprocessors work. This same principle is used for register storage in many processors. To store a bit, you put two inverters in a loop and it will hold a value. If you put a 0 on the top, the inverter puts a 1 to the bottom, then the other inverter puts a 0 back on top, so it's a stable loop. Likewise, you can put a 1 on the top and it makes a stable loop. So you can store one bit, either a 0 or a 1. To make this useful, you add a couple of transistors so you can select this particular bit. And then you add some wires so you can read and write the bit. So now this is what it looks like when you implement it in silicon. As we saw before, each inverter becomes 2 transistors. So now you have 6 transistors to store one bit in your register. The arrows show how each transistor maps to a structure in the silicon. Now, if you repeat that circuit 8 times, you've built an 8-bit register. Here, the bits have been stacked up to make your register. Now, repeat that 16 times and you have 16 registers. And that part in the middle where it's irregular, that's where the data bus is connected. Now, here's the whole die of the nanoprocessor. The registers that we just looked at are highlighted in red. So you can see that we've already reverse engineered a big chunk of the chip. And you can see that many other parts of the chip use the same principle, where a block of circuitry is repeated multiple times. For 8-bit processor, blocks are repeated 8 times, such as in the data buffers and in the ALU. On the other hand, the instruction decode circuitry at the top is much more random looking because every instruction is different. So that takes more work to figure out how it works. Now, I'll move on to something more advanced, the field programmable gate array, the FPGA, which we just heard about. I expect some of you have used FPGAs. The idea is that you can program an FPGA to implement arbitrary logic, So it's very flexible. You design the gates, the flip-flops, and the connections you want using a software tool. Nowadays, that would be Verilog or VHDL. Then the design is compiled into a file called the bitstream, and then you load the bitstream into your FPGA, and the FPGA implements the circuit you want. So here's a diagram of how an FPGA is constructed. The one I'm looking at is a very simple one with an 8x8 grid of configurable logic blocks, or CLBs, which are shown in blue. Each CLB can be programmed with an arbitrary logic function, and then you can hook a flip-flop in there. And then the CLBs are surrounded by a routing network that you can program to wire together the CLBs however you need. And then you can also route the CLBs to the IO pins, which I've shown in yellow here. Now, the funny thing is, if you look on the die, the FPGA doesn't look like that at all. You don't see CLBs surrounded by routing. Instead, a CLB and the routing are combined into a single block, which is called a tile. Now, I've outlined a tile in red on the left, and then shown what a tile looks like under the microscope on the right. So the FPGA is basically built by combining tiles together. Now, on the right, you can see the tile has routing matrices and switches at the top. At the bottom, it has the lookup tables that implement arbitrary logic functions. And what I'd like to focus on now is the configuration memory cells, the green boxes. Each tile has over 100 memory cells. These memory cells are how you program an FPGA. Each memory cell controls some aspect of the tile. So now, if we zoom in on the tile, we can see 8 bits of memory cells, which I've outlined in red. Now in the middle, I show one of these cells with the metal layers removed so you can see the transistors underneath. And then the schematic shows that there are 5 transistors to store each bit. It has 2 inverters hooked up in a loop, very much like the nanoprocessor. Now each memory cell holds 1 bit of FPGA configuration and controls a nearby circuit in the tile. For instance, a configuration bit might connect 2 lines together for routing, or you might use 8 bits for one of your lookup tables for a logic function. Now, you might wonder how an FPGA implements an arbitrary logic function. Now, the trick is it uses a lookup table, an LUT. Now, suppose you want to implement A XOR B XOR C. Now, you can write out the truth table for this function, which gives you the 8 values on the right. Now, if you want to implement that function in FPGA, you load these 8 bits into the FPGA. Then the FPGA uses a tree of multiplexers to select the 1 bit out of these 8 based on the values of A, B, and C. So if you want a different function, you can load different bits into the table. Now, if we look under the microscope at the die, we can actually see the memory cells that hold this lookup table and the multiplexers that select the output. This photo shows the memory cells for 2 bits in the table and the multiplexer transistors that select between these bits. So by knowing where these bits are on the die, we can use that to help reverse engineer the format that the FPGA uses for its programming. Now here's an example of how the memory cells control routing. This is a switch matrix. This takes 8 lines in the FPGA and lets you connect them together almost arbitrarily. Now it has 9 memory cells at the top and 9 at the bottom. And so I've highlighted one of the memory cells. Each memory cell controls a transistor. The transistor indicated with the arrow makes a connection between line 5 and line 1. Thus, if you want to route together lines 5 and line 1, the bit stream will store a 1 in the highlighted memory cell, the transistor turns on, and those lines are connected. Likewise, you can use the other memory cells to connect other lines together, and that's how an FPGA gets wired up however you want. To wrap up the FPGA, this shows how one tile is put into an 8x8 grid of tiles as shown here. A modern FPGA has many more tiles, of course. So by experimenting with FPGA and examining the circuitry under the microscope, we can determine how the bits in the bit stream control the tile. You can see some gaps between tiles for power and buffering. Because this tile layout is somewhat irregular, the bit stream is also somewhat irregular. So now I'm currently using this analysis to reverse engineer the bitstream format as part of an open source FPGA project. So next I'd like to talk about the interesting things you can find in the chip's ROM. By looking at the die, you can often read out the ROM contents as other speakers have described earlier today. Now, first I'll start with the Sinclair Scientific Calculator. Now, back in the 1970s, Texas Instruments built a simple 4-function calculator. This used a chip that crammed the code for the calculator into just 320 words of ROM. This calculator, all it could do was add, subtract, multiply, and divide. Now, Sinclair came along and they reprogrammed this chip to make it into a scientific calculator. Now, this raises the question of how is it even possible that you could take this simple chip and then fit trigonometry and log functions into it when it can only barely handle basic math? So I reverse engineered the chip to find out what was going on. Here's a die photo of the chip from John McMaster. You can see it has your basic features of a processor, registers, arithmetic logic unit, control logic. But since it's in a calculator, there are also some things that are different. It's doing decimal arithmetic using a 4-bit ALU. And down in the bottom left, you can see a decoder where it drives the 7-segment LED display. Now, what I'm going to focus on is the instruction ROM in the lower center. The ROM holds the 320 instructions that make up the calculator's code. Now, if you zoom in, you can see the bits formed from individual transistors, these rectangular boxes on the right. Fortunately, this is a simple process. It doesn't use the implant technology that John McMaster was looking at, so we don't have to use hydrofluoric acid. We can just look under the microscope and see the pattern and read out the calculator's code. So I read out the code, reverse engineered the instruction set and the architecture, and then I built a simulator to run the code. And from that, I could figure out how the algorithms work. Now, the trick is they used algorithms that are slow and very inaccurate, but also very compact. If you want to do a trig operation, you do repeated rotations by 1/1000th of a radian. Now, this means the bigger the angle, the slower the operation. So if you do sine of a big angle, it takes a long time. And log is based on repeatedly multiplying by 0.99. Now, these values are special because they're very easy to do with decimal arithmetic. To do a rotation, you're basically dividing by 1,000, which is just shifting by 3 digits and doing an add. Multiplying by 0.99 is really just dividing by 100 and then subtracting. And with decimal arithmetic, that's just a fast shift. So these steps are repeated many times, which is why it's slow and inaccurate, but it lets them fit these relatively complicated operations into the ROM. And I've got a link for the simulator if you want to look at it in more detail. Next, the Intel 8086 is a very important processor. You're probably watching this talk right now on a descendant of the 8086, unless of course you're on your phone. Now on the left is how the 8086 looks under the microscope. You can see it's much more complex than the other microprocessors I've looked at because it has 29,000 transistors. Now on the right, I've removed the metal layer and the polysilicon so you can see these transistors. This makes the functional groups more visible. Again, you have the ALU, registers, instruction decoding, and so forth. But I'll focus on the microcode ROM in the lower right. This was the first processor that Intel used microcode for. Now, if you zoom in on the ROM and then zoom in further, you can see individual transistors. I've circled 3 of them. The white stripes are the gates. So if there's a transistor there, it's a 1-bit. If there's no transistor, it's a 0-bit. Basically the same as Peter discussed. So we can read up the 10 kilobits of microcode. I also dug up some Intel patents that had some information about the microcode. And then 8086 expert Andrew Jenner took the die photos and this data and figured out how the 8086 microcode works. So now we know exactly what the 8086 is doing internally. And Andrew found a couple of undocumented instructions in the process. So that's pretty cool. Next, the 8087 is the floating point coprocessor that went with the 8086. Now this chip is important because it basically created the modern floating point standard. Now I'm going to focus on the constant ROM in the lower left. This holds constants that the chip needed for calculating logs and trig functions, Cordic algorithms, and so forth. Now this chip, of course, is much more accurate than the Sinclair Scientific calculator. Now if you zoom in on the constant ROM, the transistors show up as green and red stripes. So now we can read out the bits from the ROM by looking at these transistors. The bits are interleaved in groups of 2, which is a little tricky to figure out. So there's some gaps. So you can see here the constant 11001001, and it continues on for 67 bits. Now the cool thing is this number is actually the binary value of pi. So we can look at the die and actually see pi there on the die. I think that's pretty neat. The next thing I'd like to talk about is my adventures with counterfeit chips. There are a lot of counterfeit chips out there, which has a big impact on hardware security. There's a lot of problems with the chip supply chain, especially if your supply chain is eBay. So on the left is a 64-bit RAM chip from Intel. This was Intel's very first product. I've popped off the lid of the chip so you can see the die inside. On the right is a similar 64-bit RAM chip that a friend of mine, Robert Barrett, got on eBay. Now he looked inside, and the picture on the right is what he found. On the left is the Intel chip. You can see a matrix of 64 cells storing 64 bits, but the chip on the right is entirely different. So what is going on here? Well, looking closely, I noticed the chip on the right contains small ROMs. Very strange if they're selling it as a RAM chip. So I've zoomed in on a ROM. I was able to pull the data out of the ROM, and I found it encoded a sine wave. Not what you'd expect. So after more investigation, I determined that the chip was really a tone generator for old touch-tone phones, and the ROMs held the sine waves that it generated and fed into D to A converters. So I was able to prove that someone was relabeling obsolete phone chips and selling them as memory chips. Robert contacted the seller, who said that the chip must have been damaged during shipping. So pack your chips carefully, or they might turn into touch-tone phone chips if they get knocked around. Next, I was looking at the 8086, so I bought a bunch of them for die photos. Now the one in this picture looks like a normal 8086, but when I opened it up, I found something entirely different, as you can see on the right. The chip on the right is a ULA, an uncommitted logic array, a semi-custom chip from the 1980s. It was relabeled as an 8086 so they could make $3.80 off an otherwise worthless chip. Not much profit, but I guess it's better than nothing. So there we go, another fake. Now finally, I was helping Curious Mark fix an old HewlettPackard real-time clock module. Now this module is pretty bizarre. Back then they didn't have clock chips, so what they did is they took the chip from a Texas Instruments LED wristwatch, which was repackaged as a DIP chip. And you can see it's controlled by our friend the Nanoprocessor. To read the time, the Nanoprocessor looks at the 7-segment display outputs to figure out what the digits are. It's actually looking at the LED outputs. And to set the time, the Nanoprocessor simulates pressing the watch. It presses the watch buttons to advance the time. So it's kind of kludgy, but that's what they had back then to work with. In any case, the TI watch chip didn't work, so Mark ordered some replacements from a seller on eBay, but those didn't work either. So we figured out the replacements were probably counterfeit, so we opened up a genuine chip and a replacement, and here's what we found. Both chips are the same, except for the color, which is just part of the decapping and doesn't really matter. We studied the chips more carefully under the microscope and discovered they were genuine. It turned out that problems with HP clock modules were elsewhere. So sometimes the chips you think are most likely to be counterfeit are the ones that turn out to be genuine. And by looking under the microscope, we can find out. Now finally, I'd like to talk about how you can get involved with chip reverse engineering yourself. Now the first step is, how do you get inside the chip? Experts like John McMaster dissolve the epoxy using sulfuric and nitric acid. You know, that's a bit too intense for me because I don't want to dissolve my lungs or end up with a super fun toxic waste site. So instead what I do is focus on chips that you can open without acid. And you can get chips in metal cans on eBay for a few dollars, and you can open them with a hacksaw, or you can get a jeweler's saw, which is like a hacksaw but works better. Other chips have a metal lid that you can pop off with a chisel, and ceramic chips like this 8008, just also you can pop the 2 layers apart with a chisel. So nice and safe. Now once you have the chips, how do you get the photos? Now, the secret is a metallurgical microscope. Now this is a special type of microscope. And a normal biological microscope shines the light from below, which works okay with cells, but not so good for opaque ICs. A metallurgical microscope, on the other hand, has this big goofy light unit, the black thing on the right, that shines light down through the lens so you can illuminate the chip very clearly. Now, even if you just have a regular microscope, you can still look at chips, and I encourage you to do so. But the metallurgical microscope works a whole lot better, as you can see with this 741 op amp. Now you can spend a lot of money on microscopes, but I got mine on eBay for a couple $100. Now, once you have the microscope to make an image, I take a bunch of photos, sometimes dozens, sometimes over 100, and then I stitch them together into a high resolution image with a program called Hugin. Now there's a bit of a learning curve here. At first, when I tried to stitch together my photos, I ended up with this Cubist Picasso style image. Now, one tip is you have to overlap images a lot more than you expect so that the software can match them up. When I started, I wanted to be efficient and overlap images as little as possible, but that's just a recipe for disaster. So anyway, once you get your photos stitched together, here's what you get. This chip is a Motorola interface chip that was used in the Apple I. Now, it's often hard to see what's going on because of the metal layer. John McMaster talked about using hydrofluoric acid, but I prefer household chemicals. You can get armor glass etching cream at a craft store, and it will dissolve the oxide layer. And once the oxide is removed, you can dissolve the metal with hydrochloric acid. This you can get at the hardware store in the pool supply section. So this shows a chip with the metal layer, and then after you've dissolved the metal layer, so you can see what's underneath. So, but what if you don't have a microscope at all? Now you can still download dye photos from the internet and do reverse engineering on that. Here are some sources of photos. You can download an interesting image and see what you can figure out. So reverse engineering, it's really something that you don't need a whole lot of specialized equipment to do. You can try it out for yourself. So that's the end. Go out and reverse engineer some chips. Thank you. And if you want a link to the slides, it's on the slide here.
Thank you so much, Ken. We have a few questions. Let me.
Okay.
Hold on. Okay. This is.
All right, I'm ready for questions. I haven't been watching the chat, so.
Yeah. Did you ever
away.
find the cause of the famous ghost in the machine, in the Sprinkler calculator?
I'm not familiar with the ghost in the machine. Maybe we can talk about that in the breakout room.
All right. Then there is some other chat to me. Okay, I think this is a comment, but the seller claimed the chip was damaged in shipping. I think maybe to a reference of some of your slides.
Yeah, I mean, obviously it was a counterfeit chip, but they claimed shipping damage, so they refunded the money. And I don't know whether the seller was actually aware it was counterfeit or if the problem was earlier in the whoever supplied them with the chip.
Is there a brand of microscope you recommend?
So I use AM scope, which is basically a cheap model of scope. John McMaster has some suggestions on more high-end scopes.
All right. Have you come across any chips which are backdoored?
I haven't seen any backdoors. The chips I'm looking at are pretty old chips, so before backdoors were really a thing. And transistors were also, they had to, every transistor was important, so there wasn't a lot of room for putting in backdoors. Actually, one interesting thing is the Z80. Now what they did with that is they didn't want people to be able to look under the microscope and then copy the chip. They didn't want other manufacturers to rip it off. So what they did is they used implants to make transistors that looked like they were really transistors, but they were stuck on. So if you just copied what you saw under the microscope, you ended up with a chip that almost worked, but not quite. So they had about 7 or 8 of these trapped transistors in the Z80. And they put them in very, very maliciously. Like, it looked like normal circuitry at first, but if you under certain conditions, things would go wrong. And so by studying the chip, I was able to find about 5 of the 7 traps.
All right, interesting. Do you have any plans, desires to make Visual 6502 ESC SIMs to the nanoprocessor and 8086?
So the 8086 is probably too complicated to show every transistor visual 6502. I'm working with someone to do a simulator of the 8008, which I think will be interesting because it's simple enough that you can actually understand everything that's going on.
All right. Okay, there are a few more questions. How do you identify these pattern of gates transistors? Seems so tricky. Something you could refer to make it a bit easier to understand these patterns. And by the way, amazing work.
So, yeah. So I actually have some software that I use to help me understand the circuits. Basically, I trace out the layers of the chip into polygons, and then I feed this into a program I made that figures out where the polygons overlap, and that shows you where the transistors are. And then it collects a group of transistors into gates. So then I can understand the chip at more of a gate level than trying to figure out transistors. I've also done a lot of just drawing out on paper which transistor is connected to which, but that gets tedious very fast.
Okay. What is the level of difficulty as the node size decreases along with materials?
So there's a reason that I only look at things up till about 1980, because that's when things start to get pretty difficult under the microscope. The FPGA was much more difficult because it has two metal layers rather than one, which makes things much harder because it's unclear what metal layer is doing what. I had to get John McMaster to help me out with his electron microscope there. And then by the 1990s, your features are down to the size of light waves, so the microscope doesn't really help you out.
All right. Looks like John has most of the gadgets that we all need.
So somebody asked about the poster behind me. This is the Texas Instruments 1795. And so this is an 8-bit processor that was built before the 8008. Texas Instruments and Intel were both trying to build 8-bit processors for this company called DataPoint. Texas Instruments beat Intel, but DataPoint decided they didn't want to use either chip. Intel went on to create the microprocessor industry. Texas Instruments decided to just discard the chip and move into calculators. So this is really a chip that shows what could have happened with history. If Texas Instruments had moved forward and marketed this better, they would probably be Intel now.
Okay. I see some comments about the ghost, the calculator. How have you opened 8085 MCU?
I haven't opened the 8085, but I have some die photos from somebody else that I've studied.
Okay. I believe, do you need oil immersion's 100x objective though?
No, I don't need oil immersion for the ones that I've been looking at.
Okay, Dattatray has a comment or a question, I believe. Like to see some instruction decoder of 8085.
So, yeah, that might be something I look at in the future.
All right. I think that's it for the questions over here.
Right, well, thank you for the questions. Those are good questions.
All right. Thanks, Ken. It was amazing to hear you speak. Well, friends, if you would like to know more about Ken's research, please do check out his blog, write2.com. Some fantastic material has always been posted over there. And this presentation, along with the video recording, would be uploaded on our website and on the YouTube channel. So that's it then.
All right.